do now, we want to just get a bit out of these details, and we want to start using neural networks. Let's start with one first problem where we have an MLP for the binary classification task. So what I am showing you here, these are samples coming from MNIST dataset. And have you ever seen MNIST before? Do you know what is MNIST? So MNIST is a dataset, a labeled dataset containing lots of images. The images are 28 by 28. We're going to talk about those famous datasets shortly in 1 week or so. And every single of them is one 28 by 28 sample, and image. And that image is image of a handwritten digit. So they have actually gone outside as kids to write down a digit, 0, 1 to 9, right? And they collected those samples. They just made it uniform 28 by 28. It's a grayscale picture, so it's basically just one channel, right? And then every single of them is labeled. So they see it's 0, they say this is 0, right? This is handwritten 1, so the label is 1, and so on. Now, what we want to do classification. One question, do you see properly? Oh no, it's too much. Oh no. Okay. Is it okay, or no, I needed this one. Sorry. So yeah, what we want to do the classification. So we want to build one neural network which is taking the pixels of this 28 by 28 image as the input, and then it's going to give you back the class. But to just start with, I am considering a very simple case. The case of binary classification, it means that I'm going to look at the image. I'm going to say whether this is handwritten 2, or it's digit 2, or not, right? It's anything else. So you have only two classes. These two classes are basically 2 and non-2. So you're going to get your data set, so you're going to collect a bunch of samples from MNIST. These X's are the images, right? And you do know how you can present one image as a vector, right? We talked about it before. It's 28 by 28. It's basically 732 different pixels, right? And then you just list them as a list. This is your input, right? These pixel values are between 0 and 255, right? And if you wish, you can actually normalize it as well, right? So this is going to be your data sample, and then this V is essentially your label. So this guy is the image, the pixel vector, and this V is one binary label. So it's 0 if your image is a digit anything but 2. It's 1 when this is image of 2. Okay? Everybody's cool? So now what you want to do, you want to train a neural network such that this neural network is able to look at this image and tell you the right label, right? Whether this is 2 or not. Okay, so you need to build one neural network, so we're going to build one MLP, and we need to just specify hyperparameters there first, right? Now, I'm going to tell you, let's have this particular architecture with 2 hidden layers. If you have 2 hidden layers, then you have depth 3. This is definitely a deep neural network. It's not shallow, right? The depth is more than 2. And yeah, this is one hyperparameter that you set. You need to also specify the width of every layer, right? So you need to specify the width of every layer. You go ahead and you do it. Now, as we're going to see through semester, the typical way of doing it is that when you start with your image, you start making lots of features. So you're going to have your first hidden layer quite large. The main reason is that you want to have as much computation as possible on your input, right? Now these features are the features which probably one of them is catching what you want, right? Or maybe some of them are catching what you want, right? And then when you have these guys, then you can gradually start to reduce the width, right? So you can go for a smaller width, and finally you can go for width 1, which is your output. Okay? We're going to see it gradually through this chapter and chapter 4 when you do CNNs. Now, We need to also specify the activation for the hidden neurons. Well, you can just set all of them to be ReLU. As I told you, this is a very safe and common choice. So we're going to do that. But one question, can I use still ReLU at the output of my neural network? So for the output layer, can I use a neuron with ReLU activation? Think about the problem we have. What kind of problem we have? It's a binary classification, right? So what do we need to have at the output? Either 0 or 1, right? Because we want our neural network to tell us whether this is image of 2 or not, right? So the output should be something that gives me 0 and 1. And what can I use? Right now, you can only use perceptron, right? So I'm going to have everybody activated with ReLU, but the last guy, the output guy, to be activated by perceptron, no problem, okay? So this is going to be how your neural network looks like, right? So this is your input. This input is containing all the pixels of your MNIST, right? 732 different pixels. You're going to put them from here to here, right? Then these are going to the first hidden layer. You're going to compute a bunch of features. Maybe you can go even higher, 1,000, who cares, right? And then once you computed that, then you can drop it lower, right? And once you dropped it lower, you can finally compute the perceptron output, right? And this perceptron output is definitely something either 0 or 1, right? Now, in practice, if you want to solve this problem, you definitely do not go for 1,000 hidden layer. Actually, you go probably for 128 or even 64. So you're actually shrinking a bit here. But the reason is that the problem we're now talking about is extremely simple, right? It's very simple to find out whether an image is 2 or not. But the typical approach when you have a kind of complicated problem is to just expand this first hidden layer. We're going to see it over and over. Okay, now that I have everything set up, now I need one loss function to be able to compute the loss when I am training my model. And this is going to be my loss function. So the loss function is essentially looking at the output of my neural network. So I'm going to put the image at the input. It's going to do all the computations. I'm going to see one number at the output, right? That is either 0 or 1, right? Now I'm looking at this number. I compare it to the true label, which is again 0 or 1, right? I'm going to check if they are the same, no error. If they are different, I'm going to set an error, right? And you do know what does empirical risk represent in this case. What is that? Error rate, right? Number of errors divided by the total number of samples you have is basically what the fraction of time, the ratio that your neural network is doing misclassification. And you start with one model which has very high misclassification rate, but gradually you start to reduce it when you use gradient descent to train it, right? Okay, great. Now, I told you when we started that actually using this loss and having a perceptron is not a cool idea, right? And then you probably know this right now, why this is not a cool idea. You can guess, right? What is the issue here? Is that they are not differentiable, right? You cannot take the gradient, so this is going to be the problem. But since we are going to use backpropagation, let's take a look at the backpropagation and see where the issue is going to happen. So this is the way that you are going to do your backpropagation, right? You're going to get one sample, X, one image. This goes at the input. You're going to compute the first bunch of features. You activate the second round, activate the last output, and you activate it. This is either 0 or 1, right? And now if you computed everything, these numbers are a bunch of real valued numbers, right? But then at the end of the day, you are going to compute the gradient, right? This means that you have this guy, you get this value. These are a bunch of numbers, right? These are again a bunch of activated ones, so all of them in Y1 are non-negative, right? They are either 0 or positive because they have passed through ReLU, right? And so on for Z2, Y2, Z3. But when you get into Y3, this Y3 is either 0 or 1, right? And also the loss is the same thing, right? It's either 0 or 1, right? Now if you want to move back, you need to have this, you need to have this dual function L dot, right? The derivative of your loss function. Or you need to have the derivative of your step function here. Because the way that you are activating from Z3 to Y3 is going to be the derivative, right? The derivative is the step function, so the way that you go back is the derivative of that step function, right? Now, you can see that these guys, L dot and S dot, are actually making you trouble, right? Because they do not exist. And it is not only the problem that they do not exist theoretically. Maybe you would say, okay, I don't know, the derivative of the step function, the issue is only happening at the point 0, right? This is the point where you have the jump. There is no derivative, right? Maybe you define the gradient at that point to be, I don't know, plus 10. It's okay. You would say, okay, I approximate plus infinity to be plus 10, right? I define it this way. But even if you define it this way, the issue is that anywhere but that point, you don't have any gradient, right? Anywhere else, the gradient is defined, and that is 0, right? Same thing happens to the loss function, right? When your loss function is changing at one point, at the input, which is the y3, this is going to, I mean, you can define that particular singular point. You can define one gradient. But the issue is that anywhere else, your loss is not changing, right? So if I give the loss to this, if I give y3, and I set y3 to be not necessarily 0, 1, this is any number, right? This is going to just give me non-zero loss when this is not the exact label, right? Any other value is going, it's going to give me 0 loss when this is not the exact, when this is the exact label, right? Anywhere else is always going to be 1, right? And you take the gradient that is again 0, right? So the issue that is going to happen is not simply that we cannot define it, because we could be a bit relaxed, flexible, and define some numbers, right? But the issue is that most of the time the guy you see here, S dot and L dot, are 0. If they are 0, what's going to happen to the whole gradient? It's going to be 0, right? This is 0, everything else do not matter, right? S dot is 0, everything else is 0, right? So this is the challenge. The guy who is carrying information in this neural network for you is gradient, right? The gradient is the only guy helping you understand where to go. And as long as one of them gets 0 or very small, everybody gonna get small, right? Because they're gonna get multiplied together. So this is the key issue that you're gonna have here, right? So if you do the gradient descent, you need to just take these derivatives, and these derivatives are going to be 0 most of the time, almost always, and this means that all the time your gradient is 0. You never update, right? You start with a bunch of weights. This is going to be that forever, right? Everybody's cool? Questions? Okay. So if you have no problem, if you got the idea, now the question is that how we can get rid of this issue, right? Any idea how I can do resolve the issue? Let's start first with the perceptron at the output. The guy who is making the trouble is the activation, the step function, right? Maybe I can go ahead and replace it with something else, right? This guy is the step function. You see it, right? As I told you, it has no gradient. Bad guy, right? Everywhere 0, the only place I can define something is 0, and that one is actually useless, right? But this other guy is the sigmoid function, right? We talked about it when we started with neural networks, right? And this guy has pretty much the same property. So if x is extremely small, this is pretty much 0. If x is extremely large, then this is pretty much 1. But in between, it's just somehow smoothly going up, right? But this guy has one unique property. That is that if I take the derivative of this guy, that derivative is never 0, right? That is definitely something, right? This means that it's going to carry some information. Of course, if x is extremely large or extremely small, then it's going to be very small. This means that it somehow tells me there is no much information, right? But when x gets smaller in amplitude, this is going to get larger and larger. So it's a better kind of activation. You see that? So this is a better idea to go for this guy. So what I'm going to do, I'm going to replace my step function with sigmoid to get rid of that back issue in the backpropagation, right? To carry some gradient backwards. Everybody's cool? Okay, great. Now, so the output of network, to put at the output layer the sigmoid activation. Now, if I put the sigmoid activation, let's think about what's going to happen at the output. So you have the calculations, the computations going on till you get to the output layer, right? Your output layer is first looking at every feature you had in the previous hidden layer, right? It's going to do the computation, Z3, and then you're going to activate it by a sigmoid. It passes it through a sigmoid. That is going to be a number between 0 and 1, and that is actually neither 0 nor 1, right? Because sigmoid never gets exactly that value. It just converges to that, right? Everybody's cool? So here is a new problem. The problem is that the output is not 0 or 1, right? And if it is not 0 or 1, how can I think about, or how can I talk about the input? Like I put one image, that guy goes in, and then I get one number is 0.7. So I wanted to see either 0, which says it's not 2, or 1, it says it's 2. Now, if I see one number between 0 and 1, what is your idea? What do you do? How do you interpret that? Go ahead, yes. You treat it as a probability, right? Okay, but maybe let's be a bit less concrete. So if you see this number 0.7, right, in the sigmoid, you see 0.7, this means that you are here, right? What do you take then? You would take it roughly 1, right? When it is below half, you would say, okay, maybe I can approximate it by 0, right? This sounds like an approximation, but it's okay. It's helping me with having gradients, right? So probably you think like that, and if you think like that, as your friend said, you are treating that as a probability, right? So you basically say that this Y3 that I am seeing at the output is telling me what is the chance of my label being 1, right? So it's not actually giving me the exact label. It's just telling me what is the chance of my label being 1. Everybody's cool? And it's totally fine, right? Because it's a number between 0 and 1. Non-negative number between 0 and 1 could be the probability, right? Now, if, for example, Y3 is 0.7, the chance of being 1 is 0.7. What is the chance of being 0? 0.3, right? Because the chance of both cases should be together 1, right? It's either 0 or 1, right? When the chance of 1 is 0.7, then the chance of 0 is simply 0.3. So Y3 is giving me the probability of my label being 1. This means that 1 minus Y3 is giving me the probability of my label being 0, right? Everybody's cool? Questions? Okay. Now, we have this issue resolved, so we can treat the output some way that we can have a meaning for it. But the issue, the other issue here is that how can I get rid of the issue with the loss function? So before this, I look at the output, it's either 0 or 1, I check it with a true label, right? But now I have one number, which is the chance, and how can I compare it to the true label, right? Any idea? Sorry? I didn't get, sorry. Subtracted, you can do it, yes. If you do it, then again, yeah, that makes sense, right? Yeah, you can compute the squared error. That's fine. It's a possible way. Any other way that you can treat this? Okay. Key point, I mean, what you said intuitively makes sense, but the key point here is that the label that you have right now is 0 or 1, right? It's the true label of your data. But the output you have is a probability, right? Now you need to somehow convert this true label into a probability as well, because you can compare label to label or probability to probability, right? So you need to interpret it as a probability. And you can easily do this. How you can do it? You could say, okay, say V is 1, right? So it means that I see the label, right? Before I show you, it's a random variable, right? I tell you, what is the chance of this guy being 1, right? And you tell me it's, I would say 70% it's 1, right? But now if I reveal it to you, what is the chance of it being 1 if you see 1? What is the chance? It's 1, right? When you see some random thing, it's not random anymore, right? So you see the label is 1. What does it mean? It means that the true label is 1 with the chance 1, with probability 1, right? And it's going to be 0 with probability 0, right? Now, what if you see the label v equal by 0? So if I show you the label is 0, what is the chance of that label being 1? What is it? It's 0, right? The label is 0, right? So the chance of it being 1 is simply 0, right? So when label is 1, the chance of being 1 is 1. When label is 0, the chance of being 1 is 0, right? So I could say any label v is actually a probability, right? The probability of that label being 1, right? Everybody seeing that? Questions? Everybody's cool? Okay, so the key point here is that you can interpret the true label as the probability of being 1, right? So you would say if you give me a label v, that is the probability of my label being 1. When that label is 1, the probability is 1. When the label is 0, the probability is 0. Everything's perfect, right? Everybody's cool, yeah? Okay, great. So this is a probability. Y3 is also a probability. Now you can try to make them the same, right? You could say that, okay, this is the true label, v, and then y is, again, the same nature, is again probability. I try to make y close to v each time, right? Everybody's cool? Yeah. So this is the way that you can compare these two. I mean, obviously, you are not going to use the indicator function anymore, right? There are a bunch of reasons for that. The first one is that, I mean, it doesn't have a gradient, right? This should be always your #1 issue, right? With no gradient, no learning, right? This is the first thing. But in addition to that, the key point is that this guy is never going to be anything but 1, right? Because the output of sigmoid is never either 0 or 1, right? It's just close to that, right? And you cannot actually define that function anymore. Indicator is simply always 1, right? So forget about it. Indicator doesn't make sense anymore, right? So you need to just replace it with something. Now, as your friend said, one natural choice is to just think about the squared error, right? You would say, okay, the output is y3. The true label is v. I want them to be the same, meaning that when my label is 1, I want the probability of the output to be very close to 1. When the label is 0, I want the output to be very close to 0, right? So it means that when you see image 2, then you want your neural network to give you a very high probability of being 1, right? Being 2. So it means that it tells you 99% it's 2, right? And they would say, okay, it's 2. You want to see that, right? Everybody's cool? Okay. So this is what you want to do. This is, if you use that, then you are basically computing as the empirical risk, you are computing the mean squared error, MSE, right? You compute the squared error, and then you mean it. You average it over the data, right? This is MSE. Yeah? So this is a good choice, right? It's a good choice because you have actually gradient, right? You see that this guy has a gradient, right? Everybody sees that? You can take the derivative of this guy with respect to the argument, which is y3, is going to be 2 times that bracket, right? y3 minus v. It has a gradient. Everybody is happy. Your skin is feeling better, right? Everything's cool. So you have the gradient, no issue. But this is actually not the best choice if you want to do, right? There are better choices, and the better choice is the cross-entropy. Now, what is the cross-entropy, and where does this guy shows up? Now, there are a bunch of things, a bunch of ways you can explain it. One way is that you would say, okay, I have 2 probabilities, and I want to compare them. One way is that I go ahead and compute the KL divergence between them. Kullback-Leibler divergence. I'm not going that way. You don't need it, okay? But if you were curious, you can check it out, okay? This is one way you can do it. The other way, which is equivalent to this one, you would say, oh, I'm thinking in terms of estimation, and I'm doing maximum likelihood estimation, and if you write it down, you end up with cross-entropy again, okay? Again, we're not talking about maximum likelihood in this course too much, so I'm not going this way. I'm going the computational way. What is the computational way? First of all, let's define it. I want to have y3 close to v, right? Now, let's say v equals by 1, right? So I want to have y3 being very close to 1, right? Look at this term, log of 1 over y3. When y3 is 1, what's going to be that number? What's going to be the loss? Say y3 is exactly 1. 0, right? Is log of 1, it's going to be 0. Now, if y3 has started to decrease, y3 could be only between 0 and 1, right? If it starts to decrease, what's going to happen to this term? What's going to happen to the loss? If I put y3 to be half, then 1 over half is 2. Log of 2 is more than 0, right? And you can think of log to be in the natural base. Everybody's cool? Everybody's seeing? So if I reduce y3 from 1, right, then it's going to increase. This is what I want, right? I want y3 to be 1, right? So if it is not 1, I should have loss, I should have penalty, and this is going to happen, right? Now, what if v equals by 0? Now, look at this term, 1 over 1 minus y3. If v equals by 0, I want y3 to be close to 0. So my loss should be small when I am close to 0. What's going to happen if I put y3 0 here? The loss is 0. Perfect. If I increase y3 towards 1, what's going to happen? It's going to increase, right? Because 1 minus y3 is going to be smaller than 1, right? And then 1 over that larger than 1, this log is going to be larger and larger, right? So this is the way that I am defining the cross-entropy, but some of you might have checked it out before, and you don't remember seeing this guy. You probably have seen this expression, right? And this expression is exactly the same thing. Look at that one. V is either 0 or 1, right? If I set v equal by 1, right, this second term is going to disappear because 1 minus v is 0, right? Everybody's cool? So the second term is going to disappear. The first term is going to remain. V is 1, so it's going to drop. Minus log of y3 is log of 1 over y3, right? If you set v equal by 0, the first term is going to disappear. The second term is exactly the term you have in the second line, right? So key point, when you want to compute cross-entropy, and we did it here for the binary case, we're going to do it shortly for the multi-class case, it's not a big, complicated definition. You're going to look at the probability that you have, and you're going to take the probability of that label, right? Log of 1 over that probability is your cross-entropy. Everybody sees that? Probability of, when v equals by 1, your label is 1. The probability of your label being 1 is y3. This is the one computed by your neural network. Log of 1 over that probability, right? If v equals by 0, your label is 0. The probability of your the label being 0 is 1 minus y3, right? Because y3 is giving you the probability of label 1, right? So the probability of label 0 is 1 minus y3, right? And log of 1 over that guy is again the cross-entropy, right? So it's always log of 1 over 1 probability. And what is that probability? The probability given by your neural network for the particular class that you have. Everybody's cool? Yes? Okay, great. So this is the cross-entropy. First of all, does this guy have gradient? But y3 cannot be 0, right? y3 is output of a sigmoid. It's between 0 and 1, right? So then, does it have gradient? It has gradient. It has everywhere gradient, right? So just to show you, so as I told you, you can think about KL divergence. One key point here, this is not exactly KL divergence. This is a shifted version of KL divergence. But that shifted version is shifted by the entropy of the source. And in your case, that is always a constant, so you can drop it. If you minimize this guy, you are minimizing KL divergence, okay? But this is just in case you know what is KL divergence and you're interested to know how it is connected to that one. But at the end of the day, for us, this is a loss function because when y3 is like v, it's going to be 0. When they are different, it's going to be large, right? And then it has derivative everywhere, right? So you can go ahead and take the derivative, and this is going to look like this one, right? This is log of y3 is going to be 1 over y3, right? This is log of this guy is going to be minus 1 over this guy, right? And you write it down, this is going to be your gradient. You always have gradient, right? And this y3 here is neither 0 nor 1 because it's coming out of sigmoid, right? So you never get into this trap that you have no definition of the gradient, right? Yes, go.
Did we have a specific reason why we're using this instead of something like the mean squared error? Does it diverge?
Yeah, I give you explanation next. I mean, statistically, this is going to be like, as I said, minimizing KL divergence, whereas that other one is somehow considering some weird Gaussian assumption. And it doesn't mean that that one does not converge. That one converges as well, but this is converging more strongly. So this is a statistical definition, but I'm going to explain in terms of gradient that we are interested in next slide. Questions? Everybody's cool with cross-entropy, right? So this is the guy you always use for classification. Now, why we are doing it in practice, so computationally, this guy is showing us better gradient behavior. So to just see this guy, let's look at let's compare the squared error to the cross-entropy, okay? I have a given value v, right, the true label, and now I am thinking how y3 could change, right? y3 could change somewhere between 0 and 1, right? It could be very close to 0, it could get very close to 1, or something in between, right? This is the range. And what I want to do, I want to plot this loss in terms of y3, because at the end of the day, I am going to take the gradient of this function, right? Now, let's think about the case where I have v equal by 1. If I have v equal by 1, if you look at this guy, this is going to be y minus 1 squared, right? The squared function, right? At 0, it's going to be 1, right? And going to drop here at y equal by 1, it's going to be 0, right? So it's the first half of the quadratic function. Everybody's cool? So it's good. It's going down. Obviously, it has gradient everywhere. And when you get close to y3, it's going to be pretty flat. So this is what we want, right? But if you draw this for cross-entropy, let's see what's going to happen. If I set y3 equal by 1, then as we saw, this is going to be 0, right? Everybody's cool? Yes? Now, the key point is that if I send y3 to 0, what's going to happen? It's going to be a log of 1 over roughly 0. This is a huge number, right? And this is going to go to infinity, right? So if you compare these two guys, which guy has a larger gradient? If you start training your model, say your label is 1, so you want your y3 to be close to 1, right? But it turns out that your y3 is 0.1. If you compute the gradient, which guy has larger gradient? Cross-entropy, right? If you look at this guy is crazy steep, right? Whereas this guy is slightly coming down, right? So this guy is giving you larger gradient. And this is the same case thing if you think about the other label, right? So computationally thinking, when you are computing the gradient with cross-entropy, that first gradient you compute with loss, that is much larger, right? When you are far away from the true label. So this means that the whole gradient could boost up, right? And this means that you could potentially converge to the point that you want faster, right? Everybody's clear? Now you might come back to me and tell me, oh, I can give you tons of functions having this property. And you're totally right, and all of those functions are going to do the job at the end of the day. But based on the statistical background that we have, we do know that this is a very cool function. It has lots of good properties that is going to fit into what we're doing, right? But if you want to think about it, as compared to MSE, it has much more gradient, right? Questions? Everybody's cool? Okay, so if you got no problem here, so a key point here, you are getting larger gradient because your loss is going to just penalize everything much harshly. And because of that, this seems to be a better idea, right? And if you do that, then you're going to get rid of the troubles that you had before. You actually have gradient for your loss, right? And this gradient could potentially be very large. And you also have the gradient for your last activation because sigmoid has always gradient, right? And then when you do the backpropagation, you never get stuck into 0, right? And this means that every time you're updating, you're somehow updating, right? But maybe initially you're updating very aggressively, like your weight is changing entirely, but as you get closer to what you want, that gradient is getting smaller, right? And then you are changing less. Everybody's clear? Questions? So here, now we are happy. We have a good gradient here, we have a good gradient here, and everything gonna work, right? So I hope that you are seeing this because when you think about neural network as a computational model, then the only thing matters is gradient. Okay, cool. Now, any questions? No question? Okay, now that we have figured it out, how we can deal with this, now the last thing we need to just make sure is that how we can use how we can do the inference. Say we have done the training, everything is over. Now I'm going to take one new image, right? One image from MNIST, and I see whether I want to check whether this is true or not. I'm going to give it to my neural network, right? And the neural network is going to do a bunch of computation. It's going to give me one output, right? When I look at the output, I treat that y3 to be the chance of being label 1, right? And for instance, in our example, it's going to be the chance of my image being digit 2, right? And then 1 minus y3 is essentially the chance of not being 2, right? And now if you want to do the inference, you already told me this, answered this question. How can we do it? You're going to threshold this y3, right? What is the right threshold that you're going to put? At what point you would conclude that this, I mean, given y3, for what values you would say the label is 1? y3 more than? 0.55. Half, right? You're going to say y3 more than half, I'm taking it 1. If y3 is smaller than half, I'm taking it 0, right? So basically what you're saying that I'm going to look at the output. The chance of being 2 is 0.7. The chance of being 0 is 0.3, right? And I'm taking the guy which has the maximum likelihood, right? So you're taking the maximum likelihood here, which means that you're going to just simply compare with half, right? When it's more than half, the more likelihood is given to the image 2, right? When it is less than half, then the likelihood is that this is not image 2, right? And then you just basically take the one which has the higher likelihood, right? Everybody's cool? Question?
So
yeah.
Now we're not calculating the backpropagation with the label, but the probability of label.
Right, right. When you train and everything is over, the model that you have is computing probability for you, right? But you are able out of that probability to get a conclusion, right? So for you, this is like the neural network does this, like you don't see the image, right? And this is going inside the neural network. The neural network somehow summarized the image for you. So it says the chance of being 2 is 95%, right? It would say, okay, it's 2, right? But at the end of the day, you never do anything completely deterministic. You are not 100% sure anyways, right? Any model could have error, right? Everybody's cool? Questions? No question? Okay. So if you got no question, then let's go ahead with the next part. The next part is that what's going to happen if we want to do more than 2 classes, right? Like we want to be like any normal person, we want to just work with MNIST as MNIST, right? We want to just look at the image, say whether it is 0, 1 to 9, right? So this is the multi-class classification problem, and we can, of course, do this, right? So as I told you before, any multi-class classification, you can always write it down as a sequence of binary classifications, right? So you can look at the image, MNIST image, and you would say whether this is 0 or anything else, right? If it is 0, problem is over. If it is not 0, then is it 1 or anything else, right? You can keep on going till you get to the last one, which is going to check whether it is 8 or 9, right? But if you do that, how many neural networks do you need? You need one neural network to check whether this is 0 or anything else, right? You need your second neural network to check whether this is 1 or anything else, anything more than 1. You need the next one to check whether this is 2 or anything more than 2, and so on, right? It's not practical, right? What if I have 1,000 classes, right? It doesn't make sense, right? So this is not the practical way that we do it. So we typically do it more efficiently, and the way that we do is that we already have done computations, right? So I would say that, okay, I got this image and I computed a bunch of features. After that, I processed the features over multiple hidden layers. Finally, I have a bunch of good features in this neural network, right? What are those features telling me? They're talking about the image, right? Probably, I mean, they are not understandable for me, but for the neural network, they're somehow telling it, okay, you have a lot of curvature, right? I have seen 2 circles, right? I have seen no edges, right? And then you want just one last module to look at that and tell you what is the chance of this guy being any of the digits, right? So if it has seen 2 circles, if it has seen no edges, okay, it's most probably H, right? So you have those features here, the information about the image. You only need to process them into one probability distribution, right? Which is telling you what is the chance of every single label that you have. So how we can do it? We can just replace it with one module, right? And what does this module do? It's going to look at the features that I computed up to the last hidden layer, and out of that is going to compute me a probability of every single label happening, right? Meaning that in the case of MNIST, in the example of MNIST, is going to look at the features we computed. It's going to tell me what is the chance of label B. This is digit 0, this is digit 1, digit 2, digit 9, right? Everybody's cool? You got the idea? So we have everything that we want here. Everything is cool. The only thing that we don't have is this module, right? Anyone knows what module is that? Anyone has heard of it before? This is softmax, right? Right. Softmax is the most famous one, right? Okay. Now, let's see how we can do this. This is the idea that we call it vector activation, right? And the vector activation, it simply is that instead of thinking about a single neuron, which is looking at a lot of features and compute you one number, you're going to get a kind of larger neuron, which is still is looking at lots of features, right? And then it's computing a bunch of outputs, right, at the same time. And you might tell me, oh, what is the difference to having multiple neurons stacked together? Well, there is a bit of difference here. And the difference is that this module is looking at the whole computation that you have done, and then is generating all the outputs together, right? So 2 outputs could depend on every single input, right? So you're going to see it quite soon. Oh. Okay, it has. Okay, I thought it was turned off. Okay, so you're going to do this. We're going to see the difference shortly. So the main idea in a vector activated neuron is in this form. So you're going to have you first of all have a bunch of inputs, right? So X here is an array of inputs, like your features, right? And then you do a computation on that. You do know that this means like you multiply it with a matrix, right? You're going to get a bunch of outputs. Maybe you add a bias, right, to every single computation. So this thing inside is simply one of those linear layers you have inside your neural network, right? So you get your X, and then you are going to get a C-dimensional output, right? The C-dimensional output is first transformed by this linear transform. So everything is before, right? And C is the number of classes. Know that you have this c-dimensional. You get this c-dimensional input, which is wx plus b, and then you try to just compute one nonlinear function out of it, which is again c-dimensional. This is the activated version y, right? Everybody's cool? Okay, so this is vector activation. Now, first thing first, we can just get rid of that notation, the bias. We can just stick the bias to the waist, right? As we did before. We always do that. So what we are doing here, we have one input plus dummy, and then we do lots of linear computation on that. We get the output, right? This output, wx, is essentially c-dimensional, right? And then I have this function operating on this all c inputs and computing me c outputs at the same time. Everybody's cool? Questions? So the difference to the previous one is that in the previous one you were doing entry-wise activation, right? You look at this wx, it's going to be, for example, z1, z2 to zc, right? Then the first one is just a function of z1, the first activated version, right? The second one, the second activated version, is only a function of z2 and so on, right? But now it's not the case. The first guy, y1, could be a function of all computations, right? y2 the same, and so on. Okay? Everybody's cool? Great. So this is the vector activation, and this is the way that you can think of it. So you have a bunch of linear computations. They are all going together. Now you get a bunch of computations in an array, and then you activate all of them together, meaning that every single output that you have here is a function of all of them potentially, right? And you can have this computation graph for it, right? So you have the linear transform, and then this z to y, you see here, z to y is an array to array, and it's being done by one function, right? Again, you can do backpropagation. Again, you can do everything that we have done before, but this time you should just pay attention to the fact that every single guy in the output array y depends on potentially every single guy in the input array z, right? Okay, now let me give you one particular example, basically the only example that we use in practice, and that is the softmax activation. So softmax is a vector activation. How does it work? It works like this. So you get your z. So first of all, you have all of the inputs, right? You don't care. These are the features you computed, right? You first transform them into c computations, right? That is what I'm showing by zc, right? z1, z2 to zc, right? Say you have 10 different classes. You have 10 different of the different z, right? You had originally, I don't know, 100 features. You put one linear block, which is mapping that 100-dimensional thing to 10-dimensional thing. And then you pass that 10-dimensional thing through this equation to get 10 activated versions. Everybody's cool? Now, if you want to think about one of them, so yc, the c activated guy, is going to be the exponential of the c non-activated guy, divided by sum of all of the activated ones, right? And you see it here. This is a vector activation, right? Because y, for example, 2, not only depends on z2, but it also depends on z1, z3, everybody else, right? So when you look at this equation, you cannot compute y2 unless you know all z1 to z10, right? It's different from the entry-wise case, right? In the entry-wise case, I get z1 or z2, and then I compute y2. Everybody's cool? Questions? Okay, this is softmax, and this has one key property. What's going to happen if I add up every single entry computed by softmax? If I compute all the outputs together, add all the outputs together, what's going to be? 1, right? So this is the property that we want, right? We want to compute a probability distribution, right? And this guy is giving us a probability distribution. So if you add it up over all classes, then essentially this is going to be a denominator. Nominator is going to again add up. This is the same nominator and denominator. It's going to be 1, right? Now, can any entry in softmax be negative? No, right? They are positive numbers between 0 and 1. Add up to 1 is a probability distribution. Okay? And this is what we wanted, right? We wanted to just extend to multiple classes. We said we had all the computations as before, right? We just want to have one module which looks at those features and computes us the probability of every class. And this guy can do it, right? Everybody's cool? Great. So this is the one which we're going to use for a multi-class classifier. And basically, we're going to replace the output layer with one softmax activated output layer, right? So before this, you were just computing one sigmoid, right? And that sigmoid was looking at any features, doing linear computation, computing one number between 0 and 1. Now the thing that you do, you look at the same features, but this time you do a vector computation, right? A bunch of features. And then you activate all of them by softmax. This is going to give you the probability of every class, right? Everybody's cool, yes? Great. So this is the way that we can do multi-class classification. You get all of these features, and then you do the computation, you get the output. For every class, this is basically the probability of every class happening, right? Okay, great. Now, we can do, again, the training as before, right? We can just send every single image, right? This guy goes all the way to the output. We look at the output. We try to interpret it as a probability distribution. We compare it to the true label, right? Then we compute a loss, probably cross-entropy. And then we're going to go back by backpropagation, right? So we're going to have 2-3 minutes break.